And now we're ready for competitor number 5, who is Emily Lenhardt from the School of Meteorology. The title is Measuring the Microscopic, Characterizing Clouds from Space.
For atmospheric water vapor to condense into a cloud on its own would require relative humidity values of close to 400%. These conditions are so unrealistic in our atmosphere that to condense a cloud from water vapor alone can only be done in a lab setting. In reality, each individual cloud droplet nucleates around an atmospheric aerosol. These atmospheric aerosols can come from a variety of sources, including smoke from wildfires, salt from sea spray, dust blown from deserts, and pollutants from anthropogenic sources. Not only do these aerosols act as the building blocks of clouds, but their concentrations and chemical compositions impact cloud properties, especially in terms of how clouds interact with incoming sunlight. As we have a higher concentration of atmospheric aerosols, we can nucleate more cloud droplets. And a cloud that's made up of more cloud droplets has more surfaces for incoming sunlight to reflect from. This can act as a cooling mechanism amidst our ever-warming climate. However, these interactions between clouds and aerosols are highly uncertain relative to other climate forcings. So, to reduce these uncertainties, we need to make observations. We can directly measure aerosols using aircraft-based instrumentation, and these kind of observations are very valuable and reliable. However, it's expensive to make those kinds of observations, and so their scope is limited to a few times and locations across the globe. This is where my research comes into play. I'm using an observational data set from the Southeast Atlantic, where seasonal biomass burning results in a really thick layer of smoke aerosols that interacts with a large deck of stratocumulus clouds. I'm working on increasing the amount of information we have about smoke aerosol concentrations using the fact that we can also indirectly measure them using an instrument called a LiDAR. A LiDAR is similar to a radar, but uses a downward-pointing laser to gather information about the atmosphere at multiple altitudes. Using the mathematical relationships that I'm developing between our direct and indirect observations of aerosols, we're able to calculate their concentrations from the LiDAR measurements alone. So, where we were initially limited to an single aircraft track of smoke aerosol concentrations, we're now able to calculate them in a vertically resolved way and have them over a much wider region. Through this research, we have the potential to increase our information about aerosol quantities, learn more about how they interact with clouds, and greatly reduce climate-relevant uncertainty. Thank you.